Okay, so today we want to talk about a topic from probability. We want to talk about distributions, about how numbers fall, how random numbers fall. So the distribution of a random variable is its pattern of variation. One of the things we've talked about a couple times already is that although random means in some sense not predictable, in another sense random can be very predictable. So if, for example, I flip a coin, excuse me, roll a dice, then it's true that I cannot tell you what the next dice roll will be, or the dice roll after that, or the dice roll after that. But if you observe many dice rolls, of course, you see an overall pattern emerging from the sort of apparent lack of pattern in the one at a time. So if you roll a dice, then you expect that the 1 will come up one time out of 6, the 2 will come up one time out of 6, the 3 will come up, etc., one time out of 6. So there is a pattern somehow to the way that these random numbers lay out. One time out of 6 is 1.67. So excuse me, 0.167. So we're looking here at kind of a pattern to how these numbers fall. So the distribution of a random variable is the pattern of variation. You can regard that pattern and random are in some sense opposite, but the world is a complicated place, and in some sense pattern and random are not opposite, and this is a perfect example, is that there is definitely a pattern to the randomness. If you actually roll a dice 100 times, then the 1 may come up not 16 or 17 times that you might expect, but it might come up 25 times, or it might come up 10 times. That is to say, there's a difference here between the distribution and the sample. It's kind of in some ways like the difference between climate and weather. Climate is what you expect, weather is what you get. Well, distribution is what you expect, a sample is what you get. The distribution is what will happen in theory, while a sample is what happens when you actually observe the random variable some number of times. Another example, because it's an important idea, I want to do more than one example. If you flip a penny twice, so you flip a penny twice, you could get tails and then tails. You could get tails and then heads. You could get heads and then tails. You could get heads and then heads. You might notice that 2 heads happened one time out of 4, 2 tails happened one time out of 4, but one of each happened 2 times out of 4, and that's what we're looking at here. 2 heads happen one time out of 4, 25% of the time, 0.25. 0 heads happen one time out of 4, 0.25. 1 head out of the 2 flips happened 2 times out of 4. So what we're seeing then is that a distribution doesn't mean all things are equal. A distribution can have high spots or low spots where some things are more or less likely. If you flip a penny twice, of course, and you go out and repeat that experiment 100 times, you may very well get the outcome of 2 heads instead of being 25 out of the 100 times. Instead, you get it 20 times. That's the difference between what you expect and what you actually observe. What you expect is in some sense the theoretical value, the distribution. What you actually observe is the sample, and samples vary from what you expect. You don't think they'll vary a whole lot from what you expect, but you think they'll vary somewhat from what you expect. So I want to point out 2 different kinds of distributions. The first kind, of course, you can read is discrete distributions. Sometimes there are a limited number of cases, and each of them has an associated probability. So we just saw 2 examples of that. We saw that if you roll a dice, there are 6 possibilities. You can't get 1.4. You just can't. If you flip a coin 2 times and count the number of heads, you can't get 1.75 heads. You just can't. So sometimes there are a limited number of cases, and they fall into discrete categories. And so here I have an example of falls into discrete categories. There happen to be 5 discrete categories, and like so. The category called 0 happens 0.2, so 20% of the time. The category 0.2 happens 1 time out of 10, this sort of stuff. If the random variable takes on a finite number of cases, then you call it a discrete random variables, because the possible outcomes fall into discrete chunks. Here, discrete categories, and that's one of the possibilities that can happen. The other possibility that can happen is, again, you can read the continuous distribution. So if there are many divisions, hundreds of divisions, then the curve top becomes less of a dot, 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 and more of a continuous curve. That's what we're looking at here. So we can think of this as a sort of a non-calculus explanation of what's happening here, but we can think of the many, many division cases as being essentially a continuous curve. If a random variable can take on an interval of values, then you say it's a continuous random variable. If you have a continuous random variable, it doesn't really make sense to say what's the chance of. So if, for example, you think of the continuous random variable, people's heights. So we say I'm going to measure people's heights out to the fifth decimal place. So what's the chance that somebody is 62.12345 inches tall? And the chance of that is really basically zero. Instead, what it makes sense in that context is to say something like, what's the chance that somebody is between 62 and 64 inches tall? That makes sense. So with a continuous random variable, you have to speak about intervals. With a discrete random variable, we talk about individual cases, individual categories, and then the categories, for example, on the previous slide were numbers. That's perfectly fair. But my point is that in a continuous distribution, you're talking about an interval, and a discrete distribution, you're talking about this one, this one, this one. In continuous case, what's the chance of being 62.12345 inches tall? It just doesn't make sense to talk about that. I want to give two continuous distributions. The first point of the first continuous distribution is that not every continuous distribution is the second one. So I'm introducing the first one first just to make the point that the second one, although it's special, is not the only one. So that sentence, I'm trying to capture what I'm trying to say here with the sentence, data falls how it likes. So one way that it can fall is this. It's called the exponential distribution. We're not going to worry about it, except I'm giving it as an example of not the next slide. You see it says e to the minus x there, but it doesn't really matter. So an example of this happening in practice, I call this the baby turtle graph, because everybody has seen those videos of baby turtles hatching on the beach, and they try to make their way to the ocean, and some of them don't even make it as far as the ocean, and then waiting in the ocean are all kinds of fish and seals and whatever to eat them, and then even if they make it past the seals, then they probably don't live. So what you're seeing is that there's a whole lot of baby turtles whose life is less than a year, and so after a year there's only half as many, or maybe even less baby turtles as there were at the start. And after another year there's half again, and after another year there's half again, and after another year there's half again. And although it's true that some baby turtles live to be 100 years old, isn't that wonderful, live to be 100 years old, nonetheless there's this sharp drop off. That's just simply how the data lies. That's just simply how the data falls. It doesn't, it falls the way it falls. So this is characterized by what's called the lack of memory property. In this particular case, every year, half of the baby turtles don't make it to the end of the year. So the graph, it's not like you can say, well, the half that made it through their first year are smarter, and so in general the graph kind of levels off, and they go on to each of them live 100 years. That's not the way it works. This is the case that we will work with most often, and so the point of the previous slide was mostly to point out that there are other cases. This case comes up an awful lot. It's already familiar to people, so that's a good thing too, but it isn't the only continuous curve. Okay, so the normal distribution, sometimes you might hear people call it the Gaussian distribution. The normal curve, do you see the capital N there? The normal curve, and the bell curve. That's a lowercase b because it's not named after like Alexander Graham Bell or anything. It's a bell curve. But it's lowercase, it's shaped like a bell, that's all. So this is a curve that if, for example, I said let's measure the height of every man at St. Michael's, every enrolled male student at St. Michael's, to just take an example, then we would find that the heights look like so. Now, I don't know, the heights wouldn't be centered at 0. The heights would be centered at, 5'8". I'm not too sure. But nonetheless, it would have this general shape. Most people would be pretty much average. There would be a smaller number of people who were a little bit further over here. There'd be a smaller number of people who were a little bit further here. There wouldn't be all that many people who are all that far out. Okay, so that's called a bell curve. And my point about this particular curve that I want to make before leaving the slide is that we will later on in the semester see something called a T curve. It doesn't matter now what it is, but later on in the semester we'll see something that isn't a bell curve. And at that point, I'll need to say to folks, this isn't a bell curve because. So, in order to be able to say the because, I need to say the following thing. This curve, if you go through the calculus that's necessary to go through this, and this isn't a calculus-based course, so of course we're not going to go through this, but if you do go through the calculus that's necessary to go through this curve has a specific equation. Here it is. And again, please, you are not asked to memorize this or even understand what the parts are. I'm only pointing to it because later on in the semester I'll need to say something isn't a bell curve. And in order to do so, I'll need to say it doesn't satisfy the formula. And so if I haven't shown you the formula, I can't say that. So I'm saying it now. This curve satisfies this formula. Just to have very briefly gone through so that it isn't, just not just waving a red flag at folks. Okay, so that's E. E is like a 2.718. Usually folks have some familiarity with 2.718. It's got an exponent. I'll talk about the exponent in just a minute. In front of it is the constant. So it's 1 over square root of, that's pi, the regular pi, like, 3.14 kind of pi. And there it says sigma squared, and up there it says sigma squared. That's the standard deviation of the curve. So the standard deviation, the kind of place where this curve changes from umbrella-shaped to bowl-shaped on the graph, when I got the computer to draw a graph, it put little straight lines in there. I'm not too happy with that. But here it's clearly umbrella-shaped, and here it's clearly bowl-shaped. The technical jargon is concave down, that's umbrella-shaped, concave down, and concave up, that's bowl, B-O-W-L shaped. The place where it changes from concave shape to bowl shape, this distance right here, that's sigma. That's one standard deviation unit. So there is where that appears in the formula. The other thing that appears in the formula, of course, there's a variable x, the variable x for the x-axis. The other thing that appears in the formula is mu. Mu, as you remember, mu is the middle, is the mean. Mu is the location of the high spot. So in this formula, you locate the high spot, you locate the spreadedness, and you drop it into the formula in this way. Formula was just worked at the sort of mathematical details worked out sort of in the 1930s. Sometimes when a person takes math classes, they get the feeling that it was all done kind of in the 1500s. This is 1930, so not very recent, but at least not ancient. Okay, so the sort of summary of what we talked about today is that there's kind of a paradox with randomness. Randomness, in some sense, means disordered or without pattern. That's true, but randomness doesn't entirely mean disordered and without pattern. If you roll the dice, you know that the chance of getting a 1 is 1 out of 6. That is to say, in the long run, you'll see some regular pattern to how the numbers fall. How the numbers fall is called the distribution of the random variable. There are two kinds of distributions, discrete distributions and continuous distributions. Discrete means just like rolling the dice, that you can get a 1, you can get a 2, you can get a 3, but you can't get 1.4. Continuous means the opposite. It means that you get everything over an interval. You could get, for example, people be any height from 4'6" all the way up to 7'6", or whatever is your continuous range. Okay, and then the last point is this one right here, is that we will often have occasion to look at this particular pattern of variation, and we'll explain why soon enough, but at the moment I'm just cautioning a person that this is one that we'll see an awful lot. Okay, very good. So short one today, very good.